So in today's class, we are going to discuss about the number of relations possible. As this is a JEE Advanced booster class, so I know that you people have already gone through the relation and set chapter. So you know what are the different types of relations are there. But today in our class, my prime goal is not to teach you the different kinds of relation, but to tell you how many number of such relations possible. So let's start the class. See, we all know that a relation can be of reflexive type or symmetric, anti-symmetric, transitive and equivalence relation. Now, first of all, let me tell you that there is no direct method to find out the number of transitive relation possible. So first, let me just take this thing out, because I cannot give you any method of finding the number of transitive relation possible on a set. So we will be focusing on reflexive relation, symmetric relation, anti-symmetric relation and equivalence relation. Now, first of all, just I'm giving you a little quick revision that what do we mean by reflexive relation and all other relations. Very short, quick revision. Reflexive relation is that if suppose your set A has the elements 1, 2 and 3, then your reflexive relation states that any relation which will have all those elements in pairs, that is 1, 1, 2, 2, 3, 3. These three elements, these three ordered pairs will be definitely in that relation. Other than this, there can be other ordered pairs also, doesn't matter. But these three pairs must be there. If it is so, maybe some other pairs are there. I am not concerned about that. But I am only bothered about since your A has 1, 2, 3, their ordered pairs are there. So this relation is a reflexive one. This we know. Next, what is a symmetric relation? If there is any ordered pair x comma y which is in R, that implies y comma x will also be in R. Okay? What is anti-symmetric relation? It states that if x comma y belongs to R implies y comma x does not belongs to R. And if at all x comma y belongs to R and y comma x belongs to R, then this implies your x will be equals to y. That is, in short, we will say there is no problem of taking the ordered pairs of their ordered pairs 1, 1, 2, 2, 3, 3, 4, 4, whatever. These ordered pairs with that number, I don't have any problem. That ordered pairs can come in the relation which we will call anti-symmetric. Or if 1, 2 is present in that anti-symmetric relation, then 2, 1 will never be present in that relation. Is it clear? So that is what is called your anti-symmetric relation. Transitive relation we all know, though we will not need this because we don't have any method to find out the number of transitive relation. But I'm saying the definition, that is why I'm telling you. If x comma y belongs to R and y comma z belongs to R implies x comma z must belongs to R. Okay, that is transitive relation. Now, what is equivalence relation? If we find that a relation is reflexive, symmetric, as well as transitive, then we call that relation an equivalence relation, right? Now we will know how to find out the number of reflexive, symmetric, anti-symmetric relations possible, right? So to know that, you have to understand one matrix. Suppose there is a set A which contains n elements, like, let me say A is a set of elements, say 1, 2, 3 till n, okay? Now I'm finding out a relation on set A. Therefore, your relation R is from A to A, okay? So what are the elements present in A cross A? I should say how many number of elements are present in, or you can say how many number of ordered pairs are there in A cross A. It will be obviously n into n, that is n square, right? And now see, all those ordered pairs I have written in this matrix form. Like 1, 1, 1, 2, 1, 3 till 1n, then 2, 1, 2, 2, 2, 3 till 2n, and this thing goes on. So the last row will be n1, n2, n3 till nn. Now, these are all your diagonal ordered pairs. Okay? So first thing is that total number of elements I'm writing. Take this thing as your element, this ordered pair. Each and every ordered pair is an element of this matrix. So total number of elements in the matrix is n square, and total number of diagonal elements is equals to n. Now you see, leaving this diagonal element in this matrix, we are left with the upper part, which is called your upper diagonal, and we are left with, this is called your lower diagonal. Now, how many such non-diagonal elements, this upper diagonal and lower diagonal, they are called non-diagonal elements. So, how many number of non-diagonal elements present? Non-diagonal elements. It is equals to n square minus n. Moreover, how many number of elements are there in upper diagonal or in the lower diagonal? Because the number of elements in upper diagonal and lower diagonal, they are same. So how many number of elements are there in either upper diagonal or lower diagonal? It is number of elements in upper diagonal. Or you can say in the lower diagonal, which is nothing but your n square minus n divided by 2. Okay, so this much thing that we have already constructed for this matrix. Right? Now, one by one, we will find out the total number of, relations possible. Number one, first is reflexive. How many number of reflexive relation possible? See, in reflexive relation, what is the definition? All the pairs must come. Whether the other element is coming or not, it is not my concern. It can come, it may not come. Doesn't matter to me. But all the pair elements must come. It means that all the diagonal elements of this matrix must be present in the relation. Clear? Now all these elements can come in our set, in our relation in only one way. Now these all diagonal elements are very much there in my relation. Now, we are left with how many non-diagonal elements? We are left with total non-diagonal elements is n square minus n. Now, for every such element, there is two options. There are two options. Either that element can come in my relation or it may not come. So, for every elements which are non-diagonal, they have two options. Either they can come or it may not come. So there are total n square minus n non-diagonal elements are there. Therefore, total number of reflexive relations will be 2 to the power n square minus n into 1. This 1 is for what? This 1 indicates that all the diagonal elements are coming in our relation that can come in only one way. So total number of reflexive relation possible is 2 to the power n square minus n. Is it clear or not? Okay, now let us come for how many number of symmetric relation are there or possible. How many number of symmetric, that is the maximum number of symmetric relations possible. Now see, for the symmetric relation, you simply see either the upper diagonal or lower diagonal. Either you see the upper diagonal or lower diagonal. Why I'm saying you that? Because from the upper diagonal, if I choose any element, let us say we have chosen 3, 5. By default, since it's a symmetric relation, by default, I will take 5, 3, which is actually in the lower diagonal. Clear? So simply see how many number of elements are there in the upper diagonal. The total number of elements in the upper diagonal is n square minus n by 2. For each and every element, there are two options. Either it can come in the relation or it may not come. Clear? If it comes, automatically it's, y comma x is taken from the lower diagonal. That is not my concern. That will automatically come. I have to take that one to make it symmetric. Now the question is, in how many different ways all the upper diagonal elements can come in my relation? For every element, there are two options. Therefore, the total number of choosing the elements from the upper diagonal is 2 to the power n square minus n over 2. Clear? Now the question comes about the diagonal elements. Diagonal elements, it may come, it may not come. Because if 1, 1 comes in our relation, that is the diagonal element, it still remains a symmetric. Because if 1, 1 is present, 1, 1 is again present. You can say in that way. Therefore, any diagonal element, if it comes in my relation, it becomes asymmetric. So there are n diagonal elements. Again, for every diagonal elements, there are two options. Either it can come or it may not come. So the total number of ways of selecting the diagonal elements is 2 to the power n. Therefore, total number of symmetric relation possible is 2 to the power n square plus n divided by 2. Have you understood this? Okay. So now let us come for how many number of anti-symmetric relation possible. Anti-symmetric relation possible. Okay. Now what is the definition of anti-symmetric relation? That if x, y belongs to R, implies y, x does not belongs to R. This is one part of the definition. And another part is that, yes, if any diagonal elements present, then there is no problem. Still, it will be an anti-symmetric relation. Okay, so here we have to be very careful, because when any element from the upper diagonal is coming, that should ensure us that the corresponding element of the lower diagonal is not coming. Okay? And if the diagonal elements come, I don't have any problem. So diagonal elements I will talk later on. First, let us consider about the non-diagonal elements. Now you see, let me take an example. It will be better to understand. Let me take an element in the upper diagonal, let us say 3, 4. If 3, 4 is present in my relation, that ensures what? That ensures that 4, 3 does not belongs to R. Am I correct? Now, if 3, 4 does not belongs to R, that says or that ensures us that your 4, 3 can be in R, or 4, 3 may not be in R. In both the cases, anti-symmetric relation condition will be satisfied. So, for every element in the upper diagonal, or you can consider lower diagonal, doesn't matter, but you have to choose only one, either upper diagonal or lower diagonal. So, for every element of the upper diagonal, you are having 3 choices. For any element in the upper diagonal, you are having 3 choices. What are those? That element is present in R ensures the opposite element is not present in R. This is one condition. Another one is that element does not present in R implies the corresponding element. Corresponding element means what I'm saying is if 3, 4 is there, I'm talking about the corresponding element as 4, 3. Treat in that way. Don't take it in some other meaning. So 3, 4 does not belongs to R. That ensures us 2 things. 4, 3 may belong to R or it may not belong to R. Right? In all these 3 cases, the relation will be anti-symmetric. So for every element in the upper diagonal, we are having 3 choices. Therefore, total number of relation possible for the non-diagonal elements, it will be 3 to the power n square minus n divided by 2. Because we are having n square minus n divided by 2 number of elements in the upper diagonal as well as in the lower diagonal. So for the upper diagonal, each and every element, it has 3 choices. Therefore, total number of ways of selecting this x, y and yx can be of 3 ways. So total number of ways will be 3 to the power n square minus n divided by 2. Is it clear? Now, let us come for the diagonal elements. For every diagonal elements, it can come, it may not come. Still, it remains anti-symmetric because the definition states that if the diagonal elements come in a relation, it is an anti-symmetric relation. In the diagonal elements, we are having n elements. So in total number of ways of choosing the diagonal elements is 2 to the power n. Okay? Therefore, total number of anti-symmetric relation possible is 3 to the power n square minus n by 2 into 2 to the power n. Is it clear to everyone? Absolutely? Okay. So now let us come for how many number of equivalence relation possible. Now, for finding out an equivalence maximum number of equivalence relation possible, we are having a fantastic theorem, which actually in 1930, Eric Temple Bell has given this theorem. It states that number of equivalence relation on set A, let us say A has n number of elements, has 1-to-1 correspondence to the number of ways to partition set A into non-empty subsets. What it states? It states that if your set A has n number of elements, the number of equivalent relations possible on set A will be the total number of ways of partitioning these n elements into non-empty subsets. Now, there is one condition. The condition is that the subset will be mutually exclusive and exhaustive. What do you mean by mutually exclusive? Let us say this n elements of set A, it has been partitioned in, let us say, in A1, A2, A3, for let us say A number of subsets we have formed. All are non-empty. Now it is saying mutually exclusive means for any subset if you choose, any two subsets if you choose, there will be no common element. There will be no common element. That is, these two subsets will be mutually exclusive or disjoint subsets. In any ways you can say. And what is exhaustive? The union of all those subsets will be equals to A. So this is the theorem. Now I will take to verify this theorem by taking two practical examples. Let us say we are taking a set having two elements. Let us say 1 and 2. How many number of partitions you can do in this set into non-empty subsets which are mutually exclusive and exhaustive? They can be, the partition can be like this or it can be like this. So there will be two such partitions. Now let us verify the maximum number of equivalence relation that can be formed on this set. One equivalence relation can be like only the elements 1, 1 and 2, 2 are there. Or it can be like this, 1, 1, 2, 2 are there. At the same time, 1, 2, 2, 1, they are also there. So it is again an equivalence relation. So again we are having that there are maximum two equivalence relation. And we can easily see that our Bell theorem is satisfied here. Because the total number of non-empty subsets partition that we can do is 2. And maximum number of equivalence relation that can have is 2. So the theorem is verified. I will take one more example. Let us say A is 1, 2 and 3. There are 3 elements in set A. And we are defining relation on this set A. First we will find out how many number of non-empty subsets are possible. That is, we are partitioning this set. In how many different ways we can do that? One subset can be like this. Another one can be like this. Or it can be like this. Or the partition can be like this. Or the partition can be like this. So, the total number of partitions of this set A are 1, 2, 3, 4 and 5. Now let us try to find out maximum number of equivalence relation possible on this set. One relation can be like this. The elements 1, 1, 2, 2 and 3, 3 are there. That's it. Another relation can be like this. 1, 1 is there. 2, 2. It has to be there. Otherwise it will not be a reflexive one. But in this case we are having 1, 2 and 2, 1. Okay. This is an equivalence relation. What else? This can be another equivalence relation. Yes. What else? It can be 2, 3 and 3, 2. Yes, it is an equivalence relation. What else? The equivalence relation can be like this also. It is 1, 2, 2, 1, 1, 3, 3, 1, then 2, 3, 3, 2, right? That's it. So how many number of maximum equivalence relation can be formed is 5. So again, the theorem matches this illustration. So again, I'm repeating the theorem so that we can understand it better. So whenever they ask us to find out the total number of equivalence relation possible on a given set having n elements, it is same as partitioning that set into non-empty subsets which are mutually exclusive and exhaustive. Clear? And we can easily see that actually matches. That is the total number of equivalence relation, or we can say the maximum number of equivalence relation is same as the number of partitions so formed. And this partition is what called your Bell number. We denote this by Bn. This is what? This is called your Bell number. So what is Bell number in one word? It is nothing but partitioning n elements in a set into non-empty subsets which are mutually exclusive and exhaustive. That's it. And this Bell number will be equals to the total maximum number of equivalence relation. Is it clear? Now there is a recurrence relation of this Bell number, which is Bn plus 1 is sigma r equals to 0 to n NCR BR. This is the recurrence relation of the Bell number. Okay? So it is better if we can remember this, and the initial values are B0 is 1, B1 is 1, and just now we have seen that B2 is 2, and your B3, as we got here from the second example, it is B3 is 5. That is the Bell number of number of elements 3 in a set is 5. Okay? So you see, you can find out this B3, the value is 5. We can find out this value from this recurrence relation also. Let us check it. If you want to find out B3, so you want to find out B3. B3 means it's B2 plus 1. That is, the sigma R will start from 0 till 2CR BR. So it will be what? 2C0 B0, 2C1 B1 plus 2C2 B2. 2C0 is 1, B0 is 1, 2C1 is 2, B1 is 1, 2C2 is 1, and B2 is 2. So we are getting what? 1 plus 2 plus 2. You see, we are getting the answer as 5. The same result we got here. Is it clear? So we have learned how to find out the Bell number. Even if I give you what is the Bell number 4 or what is the Bell number of 5, you can find out by using this relation. And what is the utility of finding out the Bell number? Because Bell number actually indicates the maximum number of equivalence relation possible on that set, having n number of elements. Okay, we can see one problem that actually came in JEE Main 2025 this year, 22nd January shift 1. They have already given this thing in a very sophisticated way. You see, they have said that the number of non-empty equivalence relation on the set 1, 2, 3. That is, your set is containing the elements 1, 2 and 3. How many number of non-empty equivalence relation possible? That is, they are actually asking for the bill number 3. Yes or no? They are asking for B3. So what is B3? Just now we have calculated that. It is nothing but 5. Hence option B is correct. Have you understood? So bill number is very important to find out the maximum number of equivalence relation possible on a given set. As well as we have learned here how many number of reflexive, symmetric and anti-symmetric relations possible on a given set. I hope you have enjoyed this class. See you tomorrow. Till then, take a very good care of yourself. Thank you so much.